Ullswater, home of Professor Sir Fred Hoyle, who sets the scene for a revolution in the ideas of how elements are formed in the universe.
It's quite likely that physicists, more than astronomers, were thinking about the origin of the elements way back following Bethe's 39 paper. And I think Gamow, when he began to get interested in cosmology, suddenly realized that in the early moments of the universe he had something rather like this particular idea that he would have plenty of neutrons and some protons, and so that he felt he had an almost ideal mix for producing the elements this way, and everything would get together.
Gamow believed that the universe began with a dense sea of neutrons. It immediately began to expand. The neutrons decay to make protons, and then protons and neutrons collide and can release a gamma ray and so make a deuterium nucleus, which in turn collides with another neutron, giving a gamma ray and a hydrogen-free nucleus. That nucleus can itself decay to make helium-3. Once formed, helium-3 picks up one of the remaining neutrons, emits a gamma ray, and forms helium-4. So Gamow's basic idea for making nuclei was a series of neutron absorptions in the early universe. He thought this process would be repeated and repeated until in time all the nuclei would be produced.
And when you have that sort of an idea, judging by my own experience, you see the merits of a new idea very quickly and don't see its demerits to begin with. But then I'm pretty sure what happened was that George had already seen the plus marks before he came to the minus marks, which were the gaps at lithium-5 and at beryllium-8, famous gaps at 5 and 8.
There are no stable nuclei at those masses, 5 and 8. Suppose we try to make a nucleus at mass 5. In Gamow's scheme, that would be helium-5. The neutron just bounces off because there's no way of releasing energy and making a stable nucleus. The idea of neutron capture doesn't work. It won't make helium-5, and it won't make beryllium-8 either. It was at this stage that Professor William Fowler became involved. He pioneered nuclear astrophysics at the Kellogg Laboratory, which is at Caltech in Pasadena in California.
One of the problems that we picked to work on was the question of the stability of the isotope of beryllium called beryllium-8. The reason for this is the beryllium you find in nature is beryllium-9, but because geologists and miners and chemists had never found any beryllium-8 mixed in with the beryllium-9, we rather suspected that the beryllium-8 was unstable, and we had good reasons from nuclear theory to think that it might be unstable. And so we bombarded the beryllium-9 with protons in our ion accelerators and produced deuterium and presumably beryllium-8. You can write that reaction down. Beryllium-9 plus a proton goes to beryllium-8 plus a deuteron. But instead of seeing the beryllium-8, what we saw was 2 alpha particles. In other words, the beryllium-8 broke up into 2 helium nuclei.
So here's an important process that was not included in Gamow's scheme. If 2 helium-4 nuclei collide with each other, they can make beryllium-8. But it splits apart again almost immediately.
So we showed that beryllium-8 is indeed unstable. It breaks up in something like 10 to the minus 15 seconds. But Edwin Salpeter, at Cornell, became very much interested in the application of this phenomenon to what is called helium burning in red giant stars. When Salpeter found out that we had made these measurements, he came out to Caltech in 1951, and there he did the basic work that opened up a whole new area of nuclear astrophysics for us. What Salpeter argued was that even though beryllium-8, when you make it in the laboratory, immediately breaks up into 2 alpha particles, in a red giant star, which has converted its internal hydrogen into helium, and the helium is interacting, the helium nuclei are bumping together, forming beryllium-8, break up, form again. So there's an equilibrium concentration of the beryllium-8, which Ed Salpeter could calculate. There was a time when 2 alpha particles were beryllium-8, and then he argued that during that time, a 3rd alpha particle could strike the beryllium-8 and form carbon-12, which, as you know, is a stable nucleus because you've got plenty of carbon-12 in your own body. Well, Salpeter made a calculation in which he calculated how fast, when the beryllium-8 was in its stage, how fast it would interact with the alpha particles to form the carbon-12. And although he found that it was rather slow, because he made what we call a non-resonant calculation.
So here's the situation. Salpeter felt there just had to be some way that beryllium-8 entered the cycle of nuclear reactions. Perhaps during its momentary existence, another alpha particle might come along if the densities were high enough. That would make carbon-12 and a little energy. But tunneling alone was too slow to make this work. Without very high densities so that collisions would be very frequent and very high temperatures to provide the energy, the process would never get beyond the transient formation of beryllium-8. Main sequence stars were no good for making carbon in this way. Red giant stars at first sight seem an even worse bet because they've got a cool exterior and a low average density. But the vital point is that they have a tiny core, a very tiny core, in which nuclear reactions take place. Just how dense and how hot is the core? The stellar structure problem had to be solved together with the nuclear physics problem, and this is where Fred Hoyle stepped in.
You've got to realize this is in some way a contradictory business, because when we talk about a giant star, we're talking about stars that are as big as the solar system, as the Earth's orbit around the sun, stars of enormous size. And it seemed very odd to have this turning on something that was just in the opposite direction, a little collapsed, dense thing at the center. So the problem that Martin Schwarzschild and I had to face is, how could it be that a little dense, little pea-like thing at the center of a star produced this huge envelope of distended envelope, enormously bloated outside to the star. That was the problem that we set ourselves to tackle, and it was one of the exciting moments of my career when we found things coming out right.
To become a red giant, a star evolves off the main sequence and follows a roughly vertical path, but then something stops the path short. Hoyle and Schwarzschild said it was the start of carbon formation reactions. But the vital question was, are those reactions frequent enough at the densities and temperatures inside red giants?
I happened to be invited at that time to the California Institute of Technology for a period of about 2 to 3 months. So I thought, well, I'll take all this stuff out of the files and dust it and see if by chance there's anything that Ed Salpeter's missed. Because if there is, I can, as it were, get a bit of my own back. And so I really started on this for a second time through no very worthy motive. That was how it began. But as I looked at it, I suddenly realized that with a sense of pleasure, as it were, whereas if I'd really been doing it originally, it would have been a sense of horror, that the thing didn't work, because you could put 3 helium nuclei together and make a carbon nucleus all very well. But as soon as you made the carbon nucleus, it was far easier to add, once it was made, to add another helium nucleus and make it into oxygen. So that what it seemed was that as fast as carbon was made, it was just scoured out and shifted over into oxygen. And this then created the logical problem, why is there any carbon in the world? Because as soon as you make it, it's lost. That was the problem. So I thought about this quite a bit, and I realized, because as I've already explained, I'd grown up in the laboratory, messing around in the laboratory of Rutherford in my graduate years, I realized that there was just possibly one way around this apparent impasse, and that is that if the helium nucleus, the helium reaction, the three helium nuclei getting together, went a lot faster than everybody had previously calculated, than I calculated in my first work, and as Ed Salpeter had calculated. And the one way to make it go faster is, technically in nuclear physics, is known as a resonant reaction.
Recall the shape of our nuclear potential well. The rise at the side is due to the electrical repulsion, and the dip at the center is due to the strong attractive nuclear force. Suppose this well represents the potential of an alpha particle interacting with beryllium-8. The wave representing the alpha particle, the helium-4, approaches the barrier and tunnels through. But because the energy is way below the top of the barrier, there's scarcely any wave inside the well. That means that the reaction probability would be low, and Hoyle realized that there would simply not be enough such reactions to make red giants. Now, it's always true that at higher energies, the particle will tunnel in more easily. But in addition, at certain well-defined energies, the reaction probability will be enormously enhanced. This is what's called a resonant reaction. But the energy has to be just right, a little above the resonance, and the probability is down again. So, this is the situation. Provided particle energies in stars match a resonance in the alpha beryllium reaction, the structure of red giants and the formation of carbon can be understood. It's a crucial point. Hoyle explains the way the lifetime of the state is related to the resonant cross-section for making carbon-12.
But what a resonance does now is it makes, when the particles are moving with respect to each other in complicated paths, it sets up another relationship, quite apart from the stable nucleus, which holds the particles together for a while. For temporary, it's temporary, but it's much longer. And so during this much longer period, there's a far better chance of them then finding the unusual way that will cause them to combine together into the stable nucleus. So it's basically a time factor. It allows them time for these complicated interactions to find the unusual way that forms the stable nucleus.
You see, when you put two nuclear particles together, like the beryllium-8 here and the alpha particle here, they fuse to form a compound system. And if you put them together in tune with a resonance in that compound system, then it happens a lot faster than if you're off resonance. And so Hoyle argued that at the temperature and density that he was certain occurred in red giant stars when they were burning their helium, that there therefore had to be a resonance in the beryllium-8 plus alpha reaction going to carbon-12. That translates into saying that there had to be a state in the carbon-12 nucleus, an excited state, mind you, an excited state which was just above the mass energy of beryllium-8 plus an alpha particle, and enough above so they'd have some collision energy. And he figured that out to be about 300,000 electron volts. He added that to the mass energy of beryllium-8 and the mass energy of the alpha particle, subtracted the mass energy of the carbon, and got 7.68 MeV on that very straightforward ground.
So when I got this result, I then toddled along to talk to the nuclear physicists about it. And I said, is there any chance at all that there is such a level there, such a resonance there in the carbon nucleus. And it was just at this point that I first got to know Willie Fowler.
Fred Hoyle came into the picture in 1953. He had visited Caltech before that, but in '53 he was invited to give a public lecture. And somehow or other, the Fowlers, Artie and myself, were assigned the job of entertaining the lecturer in a cocktail party and light supper before his talk, which had to be held at the Pasadena City College because it had because it had the only large enough auditorium for the well-known Fred Hoyle. I think Fred was talking on the steady state theory. Anyhow, through that lucky assignment, I got to know Fred Hoyle and invited him to come to the laboratory, and sure enough, he showed up the next day and immediately got down to business, as is characteristic of Fred. And he wanted to talk not only to me, but also to the two Laurisons and to anyone else in the laboratory who would listen to his story. And as I remember, Ward Whaling and some of the graduate students were in the room when Fred asked us, is there an excited state of the carbon-12 nucleus at 7.68 million electron volts? Well, we were all just flabbergasted. First of all, that this Englishman, this theorist, this Yorkshireman, I should say, this theorist, would come into the lab and ask us if there was specifically an excited state in carbon-12, and not only if there was one, but he specified exactly where he wanted it to be. Well, we decided to humor him, although we just felt that there was something insane going on here, and I was not convinced. Charlie Lauritsen wasn't convinced. Tommy Lauritsen wasn't convinced that there was any. We were busy. We had other things to do. What right had this Yorkshire theorist to come in our laboratory and tell us to stop everything else and look for his excited state in carbon-12? And so what actually happened was that Ward Whaling decided to give it a go.
I'd been working with this large magnetic spectrometer for charged particles, and this suggested an idea for measuring the energy of the states in carbon-12. We were going to use this reaction nitrogen-14 d-alpha carbon-12, and nitrogen-14 plus a deuteron goes to carbon-12 plus an alpha particle. By measuring the energy of the alpha particles, we'll get the energy of the excited states in carbon-12. Now, for this experiment, the deuteron beam comes down from upstairs from the accelerator, down through this pipe, and strikes a nitrogen target in the center of this chamber. Alpha particles produced in the reaction fly out in all directions. Some of them come out this way and enter the magnetic field. The charged alpha particles are bent in the magnetic field around through 180 degrees and fall on a detector down here below. The magnetic field is under our control, and as we vary the magnetic field, we vary the energy of the alpha particles that the detector will accept. This magnetic spectrometer then allows us to measure the energy of the alphas produced in this reaction. Now, when we measure the number of alphas as a function of the energy of the alphas, we expect to see a level over here corresponding to the formation of carbon-12 in its ground state. When the carbon-12 has minimum energy, the alpha particle has maximum energy. But the carbon-12 has excited states, and there's a well-known state at 4.4 MeV, and if the carbon-12 is left not in its ground state, but in the excited level, we would expect the alphas to have less energy, and we would expect to see another group of alphas over here corresponding to the 4.4 MeV level. Now, what we were looking for was another group of alphas of even less energy, corresponding to the formation of carbon-12 in this excited state at 7.68 MeV that Hoyle said we should find. So we were looking for a little group of alpha particles out here corresponding to 7.68 MeV. So we put in the nitrogen target, we bombarded with deuterons and measured the energy of the alphas that we observed. And here is a plot of our original data. Now, the ground state, the high energy alpha groups corresponding to the ground state transition in carbon-12 don't appear on this graph, but here you see a strong group of alphas at about 7 MeV, and this corresponds to the formation of carbon-12 in its 4.4 MeV excited level. And then as we go down along to lower alpha particle energies, we come to a little group here at about 4.79 MeV, and this corresponds to the formation of carbon-12 in the 7.68 MeV excited level. This is the level that we were looking for. Well, for those of us that were working on this experiment, the group of us, this was really pretty exciting. The evidence was clear and compelling, and even the skeptics had to agree that Hoyle had predicted the position of a level, of a nuclear energy level, and to the best of my knowledge, this has never happened before or since. And the group of young people that were working with me on this, well, this was a very exciting experiment.
So it took 10 days to do the experiment or thereabouts. And while 10 days might sound a short length of time, 30 years after, I can assure you that it's a pretty long time when you know that you're on the rack and you may be proved a fool any moment. And I still remember in that 10 days, the first hint I had was that they found something. There was something there. That emerged. But I kept going along to the lab and saying, but where is it? Where is it? You know, because it had to agree with my number if it was right. And they said, well, we can't really tell you that yet because we haven't got it tied down quite accurately now. But after the 10 days we had it, and the number was where it should be, within a small margin.
And so Lord Whaling and his colleagues performed an experiment in which they showed that Fred was right, and that the state was almost exactly where he had said it had to be. For example, he said 7.68 MeV. We now know it's at 7.654. So you can see how precisely Fred had calculated on purely astrophysical grounds the existence and energy of an excited state in a nucleus. And you know, to this day, nuclear theorists cannot do that using pure nuclear theory, because nuclei are compound systems of many protons and neutrons, and it's just not possible to make a straightforward calculation of where a state would be. Once we experimentalists find a state, then the theorists can explain it, you see. And we do know a great deal now, and the theory's getting better and better, but at that time it was a real tour de force.
You know, when I got this, that it fitted, then I didn't just simply say, well, hats in the air, gentlemen. I wondered what the next stage would be.